Here is arithmetic, this is geometric, and then it says here z is as small as possible. And the key thing to note here is that z is common to both the arithmetic sequence and geometric sequence. So let's let the common ratio in the geometric sequence be r, right? Then we have p is going to be equal to 1 times r, where r, q is going to be equal to r squared, and z is going to be equal to r cubed. And then similarly, if we look at the arithmetic sequence, let's let the common difference be a, right? So then x is going to be equal to 1 plus a, y is going to be equal to 1 plus 2a, and z is going to be equal to 1 plus 3a. Now it says both sequences are increasing, strictly increasing, and contain only integers. That means that a is positive and an integer. R is also going to be a positive integer. So now, since we need to set both of these expressions equal to each other, right? R cubed equals 1 plus 3a. Okay, now let's test out possible values for r. Can r be 1? Well, if r was 1, then, that's not even possible, right? Okay, if r is 2, then a is going to be a fraction. If r is 3, a is still going to be a fraction. If r is 4, then we get a valid value for a, right? Because then r becomes 64 equals 1 plus 3a. Right, 63 is going to be equal to 3a. That means a equals 21. Right, so a equals 21 and r equals 4. So with that, we have our answer, right? So the common difference is 21, and the common ratio is 4. So pretty standard problem here, right? So now it's asking x plus y plus z plus p plus q. So x plus y plus z, you can calculate z in one of two ways. I'm just going to use it using the arithmetic sequence. So x plus y plus z is going to be 3 plus 6a plus p plus q is going to be r plus r squared. And that is going to give us 149. So the final answer for problem number 11, let me write this out, is going to be E, 149. Okay, now let's move on to problem number 12. Alright, problem number 12. Carlos uses a 4-digit passcode to unlock his computer. In his passcode, exactly one digit is even, exactly one possibly different. So possibly different, that means it could also possibly be the same digit, right, is prime, and no digit is 0. So how many 4-digit passcodes satisfy these conditions? Okay, immediately the problem writers put possibly different here. That kind of gears us towards the case of 2, right? 2, what's special about 2 is it's both an even number and it's also a prime number. So this is kind of a case we have to watch out for, right? And then also, yeah, so 2 is going to be the tricky part here, right? So let's break this problem down into two cases. We'll start off with case 1. 2 is in the code. So like the number 2 is in the code. So 2 is in code. So if 2 is in the code, right, let's say we have 4 slots here. And without loss of generality, I'm going to choose to put the number 2 right here. So this satisfies the first two conditions. One digit is even, and exactly one digit is prime. That means that all of these other digits have to be odd numbers, but they can't be primes, right? So what can this digit be? It can be 1, can't be 3 because that's a prime, neither 5 or 7, but it can be 9, right? Same thing for this one and this one. So these are our possible options here, right? So if we count them up, we get 2 times 2 times 2 is going to be 2 cubed. And then there are also going to be 4 ways to choose where I can put this 2, right? I can put the 2 here or here or here. It doesn't necessarily have to be in this slot, right? So there are 4 ways I can do that. So this case here is going to give me 32 possible ways if 2 is in our passcode. Okay, now let's say 2 is not in our passcode. So let me write 32 up here, right? And now case 2 is not in password. Okay, so if 2 is not in the password, then we need a different even number and we need a different prime number. So our prime number must be odd, right? So without loss of generality again, I'm going to keep using that word, by the way. What that means is that consider this case only, but we can generalize it to overall. So if I say without loss of generality, put something here. What I'm saying is I'm counting for all the cases where if I put it here, or here, or here, or here, right? That's what without loss of generality means. So let's say 2 is not in our password now. Then I need to have exactly one even digit that is not a prime. So let's just say I put the even digit here, right? So what can this be? And no digit is 0, right? So it can't be 0, can't be 2. So our options are 4, 6, or 8. So that gives us 3 possible options. So 3 choices for this even number here, right? And then now let's choose to put the prime number here. What can the prime number be? The prime number can be 3, 5, or 7. So that's also going to give us 3 choices, right? And then our odd numbers, again, those are just going to be 2 options each, right? 2 choices for both of these. Okay, 3 times 3 times 2 times 2. So that's going to be 9 times 4, which is 36. But we also have, again, I said without loss of generality, right? I can move these even and prime numbers anywhere I wanted to. So we're going to multiply this by 4 factorial over 2 factorial, right? Because the odds are the only things repeating, and there are 2 factorial ways to arrange those amongst themselves. So this becomes 36 times 6. And that's going to give us... Oh, sorry, this is 36 times 12. My bad. I don't know why I messed that up. So this is going to be 36 times 12 here, right? So 36 times 12 plus 32. This is going to be 360 plus 72 plus 32. And that's going to give us a final answer of 464 possible codes. So the final answer for problem number 12 is going to be D, 464. Okay, now let's move on to problem 13. I know that this problem actually tripped up a lot of people because it was just like so unusual to have in like the early 15 problems, and it was like an infinite geometric sequence. So let's dive into those ways now, right? So there are 2 ways you could go about solving this problem, right? The first way is the method I used, which is the strict algebra geometric sequence, all the equations, and then like, you know, using the equations to get to some number. And the second way is just like looking at it and then, you know, using the problem to figure out the answer. So I'm going to use the first method, which is all of the geometric sequences and all of the algebra, and then I'll show the second method afterwards. So the first method, right? Let's let the outside square's side length be A. Right, let this first square have a side length of A. Let this little square right inside of it, right? The second outmost square, let that have side length B. Okay, so now let's let A over B equal some ratio R. Right, well this is going to be a number greater than 1. What is K? K is going to be equal to 1 over R, right? Because K is going to be in between 0 and 1. I don't know why, I just decided to use R instead of K. But you could also use K by saying B over A equals K. But I just did it that way, right? Okay, so now what's the area of the first, you know, ring, right? You could call these red regions here rings, right? What's the area of this first outermost ring? Well, it's going to be the area of the outermost square, this really big square, minus the area of the second biggest square. So it's just going to be A squared minus B squared. Now, if I solve for B in this fraction here, I get B equals A over R. So this becomes A squared minus A squared over R squared, right? B equals A over R, so I just squared B. So that's the area of the first ring. So A squared minus A squared over R squared. A squared minus A squared over R squared. That's the area of the first ring. Now what about the second, right? I'm going by each ring to see if we notice a pattern. Then we can maybe set up, you know, sequence. So now let's let these other squares here, this third outermost square have side length C, and the fourth outermost square have side length D, right? So B was equal to A over R, right? So by similar logic, C is going to be equal to B over R, and D is going to be equal to C over R. So B over R is going to be A over R squared, and C over R is going to be A over R cubed. So the area of our second ring is going to be C squared minus D squared, which is going to be A squared over r to the 4th minus a squared over r to the 6th. And I think now we're starting to notice the pattern here, right? It's pretty easy to predict the next few areas. We notice that we're adding 4 to the exponents every time, right? So, for example, this was a squared over r to the 0, and then we added 4. Now we can add 4 again to get a squared over r to the 8th, and then add 4 to r to the 6th to get minus a squared over r to the 10th. So this is going to be an infinite geometric sequence, right? And we know the sum of all of this infinitely many times, this whole sum here is going to be equal to 64% times a squared. 64% simplifies down to 16 over 25, right? So we can set our infinite geometric sequence formula equal to this quantity here. So let's do that now, right? So let's first take all the positive values, like anything without the negative sign, and then subtract it from the negative values. So we have a squared over r is 0, which I'll just write as a squared, right? First term minus 1 over 1 minus common ratio is the infinite sum by the infinite geometric sequence formula. The common ratio here is 1 over r to the 4th. So first term is a squared over r to the 0, which is just a squared over 1. Right, that gives me all of this, the infinite sum of this side, and I want to subtract that from the infinite sum of this side. Now the infinite sum of this side is going to be, again, first term, which is a squared over r squared, over the same thing, right? The 1 minus common ratio is going to be constant here. So a squared minus a squared over r squared over 1 minus 1 over r to the 4. This is going to be equal to 16 over 25 times a squared. Now the a squareds conveniently cancel out, and then we're only left with a simple quadratic in terms of r squared, right? So let me try to get rid of all this mess here. Right, if we cancel out the a squareds here, then they just become 1s, right? 1 minus 1 over r squared over 1 minus 1 over r to the 4th is equal to 16 over 25. So let's let r here, r squared. Let's let r squared equal x. Then we get 1 minus 1 over x over 1 minus 1 over x squared. Right, this is going to be equal to x minus 1 over x over x squared minus 1 over x squared. Multiply both the numerator and denominator by x squared to get x squared minus x on the top. X squared minus x over x squared minus 1 is equal to 16 over 25. Equals 16 over 25. Now we're going to cross multiply, and then we'll solve for x, right? And then we'll take the square root to get r. So 25x squared minus 25x is equal to 16x squared minus 16. So move the x squared over. 9x squared minus 25x plus 16 equals 0. So now let's solve for x here. So we'll use the quadratic formula, right? X is equal to negative b plus or minus the square root b squared minus 4ac. So 4 times 9 times 16 is going to be 144 times 4 all over 18. And this is going to give us 25 plus or minus 7 over 18, which equals 32 over 18, or it's going to be 18 over 18, right, or 1. Now, the ratio here obviously isn't 1, right, because the squares are decreasing. So the r squared here is going to be 32 over 18. It's not 1. So 32 over 18, we can divide both by 2 to get 16 over 9. This is equal to r squared, right? So r here is equal to 4/3. But the problem is saying that k is between 0 and 1, right? We found the ratio between the big square to the little square coming after it. But since the ratio is less than 1, it likely wants us to take the reciprocal of that. So the answer here is going to be 1 over r, which is equal to 3/4. So that is the final answer for problem number 13. Let me write that out here. So D, 3 over 4. Okay, now let me also just mention the much quicker solution, which is to note that if you just take this outer ring here and then switch the shading, right? So let's say all of this red here, this is 64% of the area, right? But if all this white here, then the white area is going to be 36% of the area, right? But what's the ratio between the area of the red stuff to the area of the white stuff? Well, that's going to be 1 over k squared, right? So 1 over k squared is going to be equal to 64% over 36%, right? And we don't really care about percentages here, just 64 over 36. And then divide both by 4, we get 16 over 9. So that means that k just straight up equals 3/4, just from that logic, right? The thing about infinite geometric sequences, or like infinite sequences in general, is you can set them equal to each other by just removing a term, right? Like switching the shading, it's still giving you the same area, but that's 36% of the area. I mean, sorry, it's a different area, but it's like the same pattern. It's just it's a smaller area, right? So that if the white shading is 36% of the area, we can just set up this really nice and quick expression here, just quickly arrive at the value k. So I thought I should just mention that because that's a really clever solution. Okay, now let's move on to problem number 14. So 6 chairs are arranged around a round table. So let's draw those. 1, 2, 3, 4, 5, 6. 2 students and 2 teachers randomly select 4 of the chairs to sit in. What is the probability that the 2 students will sit in 2 adjacent chairs and the 2 teachers will also sit in 2 adjacent chairs? Okay, so in how many ways can first let's just say the students go first, and the students they see these 6 chairs and they're like, okay, in how many ways can I choose 2 adjacent chairs for me and my friend to sit down at? Well, I can choose this pair here, this pair, right? It forms a hexagon. So the students can really choose any side of this hexagon here to sit down at. So there's 6 choices for which pair the students can pick, right? So let's say the students A and B decide to sit down here. So let me just write S A and S B, students A and student B. Now the teachers are sitting down, let's say, after the students, right? And the teachers are like, okay, well, where can we sit down now, right? Well, they can't sit down at this pair or this pair because one of the chairs is already occupied by the students, and definitely not this pair because both chairs are occupied by them. So that only leaves 1, 2, 3 possible pairs of chairs for the teachers to choose, right? So then the teachers have only 3 possible options. So then let's say the teacher picks here TA or TB, right? But I can technically arrange these 2 students, right? SA and SB can swap chairs with each other, right? And that would still count as a valid ordering. Same thing with the teachers here, right? They can always swap chairs with each other, no problem. So there are 2 ways for the students to be rearranged amongst themselves, and there are 2 ways for the teachers to be rearranged amongst themselves, right? So this gives us our first thing, which is the number of desired outcomes. Now, what's the total number of possibilities? So let's first quickly evaluate this. 6 times 3 times 4, that's just going to be 72, right? Okay, so now what's the total possible number of outcomes? So desired equals 72, right? Now, what about our total? So total meaning disregard this problem's condition. And how many ways are there for 2 students and 2 teachers to just sit down at chairs? Well, I can choose any 2 chairs, right? And 6 choose 2 ways for the students, let's say. The students, let's say, take up these 2 chairs. Then the teachers can pick from 4 chairs, so 4 choose 2. And then there are 4 factorial ways to arrange the teachers and students amongst themselves, right? So this is my total number of ways here, right? So for example, if student here, and then let's say teacher here and teacher here, right? So that's gonna be, oh, sorry, not 4 factorial, just 4, because it's the same logic as before, right? There's always gonna be 4 ways for the students and teachers to be permuted amongst themselves, right? The teachers can be rearranged in 2 ways, and the students can be arranged in 2 ways. So this gives us our total number of possible outcomes. 6 choose 2 times 4 choose 2 times 4. So 6 choose 2 is 6 times 5 over 2, which is 15. 4 choose 2 is 4 times 3 over 2, which is 6. And then times 4. 90 times 4, 360. So our probability here is going to be 72 out of 360, or 1/5. So the answer for problem number 14 here is going to be B, 1/5, or 72 out of 360, which simplifies down to that. Okay, now let's do problem number 15. Okay, so in this figure, ABEF is a rectangle, AD perpendicular to DE, AF equals 7, AB equals 1, and AD equals 5. What is the area of ABC? The thing that just immediately strikes out to me most is that these two triangles here are similar. They're both right triangles, right? That's probably why they told us this is a rectangle, because these are both right triangles then, and they're just similar by AAA. So let's draw this diagram out, right? So we have this right triangle here, and then this rectangle sort of looks like that. And then we have AF equals 7. So this here equals 7. And then AB equals 1. And AD equals 5. Okay, so let's let this side length here be x. And let's let this side length here be 7 minus x. And then let's let this side length here. Well, we already know what this side length is, right? From Pythag theorem on this triangle here. I know I did a really bad drawing. I'm sorry. That's supposed to be a right angle. So by Pythag theorem, right, let me maybe change my color if I can. Yeah. By Pythag theorem, this side length here is just going to be the square root of x squared plus 1. So then by the problem's condition, right, we have that the side length right below that is going to be 5 minus the square root of x squared plus 1. Right? Okay. And now we need to essentially set up a ratio. So we have like these two angles here are both equal to each other, right? So that implies that these two angles here are also equal to each other. So we can say the ratio between this leg and this hypotenuse is equal to 1 over the square root of x squared plus 1. So really simple quadratic here to just set up. So let's do that now, right? So we have from this these two equal angles here, we have 5 by similarity ratios, right? Minus the square root of x squared plus 1 over 7 minus x is going to be equal to what was it? Sorry, it was x over square root of x squared plus 1. And then we just cross multiply, right? 5 square root x squared plus 1 minus x squared plus 1 is equal to 7x minus x squared. So now the x squareds here are going to cancel out very conveniently. So then we're going to be left with 7x plus 1 on this side, right? So 7x, yeah, plus 1. So 7x plus 1 equals 5 square root of x squared plus 1. So 7x plus 1 equals 5 root x squared plus 1. 5 root x squared plus 1. Now we want to square both sides of this equation here, right? So let me do that now. So 49x squared plus 14x plus 1 is equal to 25x squared plus 25. So 24x squared plus 14x minus 24 equals 0. You can divide this by 2, right? We're not dividing by 0, so it's fine. So 12x squared plus 7x minus 12 equals 0. So what's x? X is going to be equal to negative 7 plus or minus the square root of 49 plus 12 squared times 4. All over 24. And that's going to be equal to negative 7 plus or minus 25 over 24. Obviously, side lengths can't be negative, so we can disregard the negative case to get 25 minus 7 over 24, or 18 over 24, or divide both by 6 over 8, or 3/4. If x is going to be equal to 3/4, then we have our base is x and our height is 1, right? So it's going to be 1/2 base times height. So our answer here is just going to be 1/2 times 3/4, which equals 3/8. So 3/8 is the final answer for problem number 15. So let me write that. A 3/8. Okay, now let's move on to problem 16. Chosen at random. What is the expected number of coins in a jar with the most coins? Okay, so we have three main cases, right? Let's say the jar with the most number of coins, it can either be 1, 2, or 3 coins inside of this jar, right? So for example, if I have 3 coins in the jar with the most coins, then 3 of the coins fell into one jar, and then the other 2 jars had no coins, right? So let's just do casework on that. So case 1, let's do 3 coins in one jar, right? Okay, so without loss of generality here, I'm gonna pick this jar to have all my coins in it, right? So now, what's the probability of all of the coins going in this jar? Well, it's gonna be 1/3 to the power of 3, right? So 1/3 cubed, which equals 1/27. But I could have chosen any one of these 3 jars, so I'm gonna multiply by 3 to get 1/9. Now, expected value is always going to be the value, which in this case is 3 coins, multiplied by the probability of that value occurring. So the expected number of coins for this case is going to be 3 times 1/9, which gives us 1/3, or 1/3. Right? Okay, now let's do 2 coins. So I'll write 1/3 to the side here. Case 2, 2 coins. Okay, so 2 coins, that means I can either have something like, oh wait, no, there's only one way, right? 2 coins in one jar and 1 coin in another. So let's say I have something like this. Without loss of generality, again, I chose these 2 jars, right? So what's the probability of this coin configuration happening? Well, there's a one, again, right, 1/3 cubed, right? But I can choose any of those 2 coins to go in this jar, right? It doesn't, it can be 1/3 cubed is like this raw probability of this happening, right? But I can really have any 2 of the 3 coins in here. So there are 3 ways I can have those 2 coins in this jar here, right? So there are 3 ways to choose the coins to go in this jar. And then there are also 3 choose 2, or 3 ways to choose the jar this happens in, right? And then we multiply by the value again, and then we get 2/9 for this one. Oh, sorry, 2/3, right? Simplified that wrong. Okay, so 2/3 probability of happening, and then we multiply by the value, which is 2 coins, to get 4/3 for this case. So 1/3 and then 4/3. Okay, and now the probability of each jar having exactly 1 coin in it, right? So case 3 is gonna be 1 coin. So 1 coin, right, something like this. So again, the raw probability of this happening is 1/27, but there are 3 factorial ways I can like permute these coins, right? Like there are 3 ways I can choose, like let's call these coins A, coin B, coin C, right? There are 3 factorial ways I can permute those coins amongst themselves, right? And yeah, that's basically it, I think. So 3 factorial times 1/27, that's going to be 6/27, which is going to be 2/9. So yeah, I think that's the answer, right? 2 plus 2 ninths. So that's going to be 3 ninths plus 12 ninths plus 2 ninths. And that should give us a final answer of 17/9 for this problem. So the final answer for problem number 16 is going to be D, 17 ninths. Okay, now problems 17 and 18 were pretty straightforward. It doesn't appear straightforward. I mean, I myself didn't even attempt problem 18 for some reason. I mean, it looked pretty intimidating, but these are actually not too bad. It's further problem numbers. So let's do problem 17 here. let n be the unique positive integer such that dividing 273,436 by n leaves a remainder of 16, and 272,760 by n leaves a remainder of 15. And we're asked to find the tens digit of n, right? So we can write this as a mod equation. So 273,436 is congruent to 16 mod n, and 272,760 is congruent to 15 mod n. Okay, now let's move the 16s and 15s over, right? So we essentially have n is congruent to 0, or n is going to be a multiple of 273,436 minus 16, which is going to minus 16, so that's going to be 273,420. So n is a multiple of 27420, and it's also a multiple of 272,745, right? Or divisor, sorry, n divides both of these numbers. So we're essentially trying to find some common divisor here, right? The greatest common divisor between 27420 and 272,745. So let's do that here, right? 27420 and 272,745. By the Euclidean algorithm, we can just take this number, any number of multiples of this number, and subtract it from this number, right? So let's subtract, and we can do the same for this number here. So let's subtract this number from this number here. So this GCD is going to be equal to the GCD of 27420. And then, oh wait, no, I should have gone the other way around. My bad. Yeah, so subtracting this number here from this number. So that's gonna be, okay, yeah, so I was missing the digit 3 in this number, so my bad. So yeah, by the Euclidean algorithm, this is gonna be equal to the GCD of this number minus this number, which is gonna be 675, and 272,745. Right. Now we can factor out the 15, I think, or 5, sorry. Right. So 675 divided by 5, that's going to be 135. So 135, right? So 5, I don't know why that took me so long. 135. And then 272,745 over 5. It's really quickly going to do that. 25, 2, 2, 4, 5, 4, 9. So 5, 4, 5, 4, 9. Okay, and so there's not really anything else common here, right? But the thing that is common is that both of these numbers here are multiples of 9. And we know they're multiples of 9 because their digits sum up to 9. Like 5 plus 3 plus 1 is a multiple of 9, right? And 5 plus 4 plus 5 plus 4 plus 9 is 27, right? That's also a multiple of 9. So 9 is going to be the GCD of this, right? So n is this whole thing, which is equal to 45. So boom, we just found our answer, right? So the tens digit of n is going to be 4. So the answer here is going to be E for problem number 17. So 17 is going to be E, which is 4. Okay, now for problem number 18. So it literally tells us, first of all, what a harmonic mean even is, which is super helpful. And then it's telling us to find the harmonic mean of all real roots of this polynomial here. So we're not going to really focus on this expansion here. Let's just focus on the general form they give us, kx squared minus 4x minus 3, right? Now, if we want a polynomial with the reciprocal of these roots, we're going to take these coefficients and essentially flip it. So the polynomial with the reciprocal, so if this polynomial here has roots r1 and r2, then this polynomial, negative 3x squared minus 4x plus k, is going to have roots, is going to have roots 1 over r1 and 1 over r2. And you can pretty easily see why if you just like apply the quadratic formula. It has a really neat derivation process. But yeah, this is something really cool that we can just right off the bat do. So by Vietta's formulas, right, it's asking us for some of reciprocals here, right? So the sum of the reciprocal of pairs of these roots here, right? So for each of these polynomials, the sum of the reciprocals of roots is going to be negative 4/3, right? Negative b over a. So that's going to be negative 4/3. So negative 4/3 is going to be the sum of each of these pairs. And so how many of these are there, right? Well, there are going to be 2025 of them. So there are 2025 of these negative 4/3 here happening, right? Okay, so let's see what our thing is going to be. Um okay. Okay, yeah. So the harmonic mean is essentially just the reciprocal of the arithmetic mean, right? So let's just quickly calculate the arithmetic mean of the sum of the reciprocal of roots, right? We know each pair of roots adds up to negative 4/3, and there are going to be 2025 of these pairs. So the total sum here is going to be negative 4/3 times 2025, and then in total there are 4,050 roots because it's a 4,050th degree polynomial. So that's going to give us negative 2/3, right? And since the harmonic mean is just the reciprocal of the arithmetic mean, the answer here is just going to be negative 3/2, or b, right? It was such a quick and easy solution that way, using Vietta's formulas. So the final answer for problem number 18 here is going to be b.